All right, we are going to work on the derivative of exponential functions. As always, whenever we are working on the derivative of any type of function, we'll definitely be using all the rules of differentiation that we have studied so far, along with some of the formulas for the derivative of exponential function. So here, for the exponential function y equal to b raised to x, so if this function in the rate is y equal to b to the x, that is the exponential function. So for this function, y equal to b to the x, and when b is positive, you know that for the exponential function, the base must be positive. Then the derivative dy over dx is equal to b raised to x multiplied to the natural log of b. So the derivative of b to the x will be b to the x multiplied by the natural log of b. So this is the general formula that we need to remember. Now, if we replace this b by the Euler's number e, then it will be derivative of e to the x. And derivative of e to the x will be e to the x, this one, multiplied by log e, and log e is 1. So 1 times e to the x is e to the x. That is why the derivative with respect to x of e to the x is e to the x. And if I want to make this a little more general, derivative with respect to x of e to the kx will be equal to, if you use the chain rule, then the derivative of e to the kx is e to the kx, and we multiply by the derivative of inside function, and derivative of k times x is k, so it will be k e to the kx. So these are the three different formulas that you need to remember while solving the problems using the, or solving the problem involving the derivative of exponential functions. Example, find the derivative of the following functions. In part A, we have y equal to 10 divided by 1 plus 2 raised to negative x. If you look at this one, it looks like a quotient. So here we have y equal to 10 over 1 plus 2 to the negative x, which looks like a quotient, but not exactly quotient. You can use quotient rule if you want, but in the numerator there is no x, so I'm not going to use the quotient rule. Instead, I'm going to rewrite it a little differently. We have 10. In the denominator, I have 1 plus 2 raised to negative x. I can write that as 1 plus 2 raised to negative x to the power negative 1. So if there is something in the denominator, we can write that as power negative 1 and write in the numerator. And by writing like this, it is easy for me to use the chain rule here with the power rule. So let's find the derivative dy over dx. Dy over dx is equal to, you can see this 10 is multiplied to that function, so it is a constant multiple. So the 10, because it is a constant multiple, it will just stay in front. Then multiplied by, if you look at this one, you have 1 plus 2 to the negative x, everything raised to power negative 1. That means you have an outside function, which is a power function, and an inside function. And whenever you have an outside function and inside function, we use the chain rule. Chain rule, in order to use the chain rule, first we have to find the derivative of outside function. That's a power rule. You bring that power in front, so negative 1 in front, and then reduce the power by 1. Here is a negative 1. If you reduce by 1, it will be negative 2. So 1 plus 2 to the negative x raised to negative 2. That is the derivative of outside function. Now we have to multiply by the derivative of inside function. So d over dx, give me a second there. Okay, d over dx of the inside function, 1 plus 2 to the negative x. So we use the chain rule in this first step. Now let's simplify this. Dy over dx is equal to, here we have 10 multiplied to negative 1, which is negative 10. So negative 10. Then here we have 1 plus 2 to the negative x raised to negative 2. If I take that to the denominator, it will be 1 plus 2 to the negative x raised to positive 2. Because if you take it to the denominator, it will be positive. If you take it to the numerator, it will be negative. Then here we multiply by the derivative of this function. So times the derivative of 1, derivative constant will be 0. So I don't have to worry about that. But this one, derivative of 2 to the negative x. Now here we are going to use our formula. This is the formula that we know. Derivative with respect to x of b to the x is equal to b to the x natural log of b. Okay, b to the x times the natural log of b. So here you can clearly see we have 2 to the negative x. So if I want to analyze this little carefully, then I can see that this is like b to the x. Derivative of b to the x is b to the x. Okay, b to the x, which is 2 to the negative x. Multiply to log b, it will be log 2. Log 2. But one important thing that you need to check here. This is just b to the x, but here we have b to the negative x. That means we have to multiply by the derivative of x because we are using the chain rule here. So the derivative of negative x is negative 1 because we use the chain rule there. In next step, it will be, let's see what it will be. dy over dx is equal to, if you look at the numerator, you have a negative 1 and here is a 10. So negative 1 multiplied to negative 10 is positive 10. And here is a log 2 multiplied to log 2, natural log 2, multiplied to 2 to the negative x. Divided by, in the denominator, I got 1 plus 2 to the negative x squared. So that is the derivative of this function which is given here. Okay, that 2 to the negative x, I just kept that in the numerator. Then you have this, when you multiply that, negative 10 multiplied to negative 1 is positive 10. Then we have a log 2. In the denominator, I have that quantity. So this is the derivative of the function y equal to 10 over 1 plus 2 to the negative x. Now, part B. In part B, we have y equal to 400 divided by 35 plus 5 multiplied to e to the negative 0.5x. This looks like a quotient and you may use the quotient rule, but there is no x in the numerator, so I'm going to rewrite this. So I'm going to write like this, 400. In the denominator, we have 35 plus 5 multiplied to e to the negative 0.5x. Because I'm taking the quantity from the denominator to numerator, I'm writing that power negative 1. Now let's differentiate. dy over dx, the derivative is equal to 400 is a constant multiple, so I can keep that as it is, 400. Now for this one, your outside function is a power function, and you have that inside function. So we use the chain rule. So when you use the chain rule, you bring this power in front, times negative 1, then reduce the power by 1. 35 plus 5 times e to the negative 0.5x. So if you reduce the power by 1, if you do minus 1, that will be negative 2. Then we multiply by the derivative of the inside function. Inside function is 35 plus 5 times e to the negative 0.5x. So we use the chain rule there. So the derivative dy over dx will be equal to, you can see here, 400 multiplied to negative 1, that is 400, but negative. And then this quantity, 35 plus 5 times e to the negative 0.5x raised to negative 2. If I take it to the denominator, it will be positive. So 35 plus 5 times e to the negative 0.5x quantity squared. Then multiply 2, we have to multiply with the derivative of this one. Derivative of 35 is 0. This is a constant multiple. 5 is multiplied to that function. So we'll keep that as it is. And then here you have the derivative of e to the kx. If you remember that formula, let me write here the second formula. Derivative with respect to x of e to the kx is k times e to the kx. So if I use that formula, in place of k, I have negative 0.5. So negative 0.5 is my k, and e to the kx, which is e to the negative 0.5x. So here we multiplied 0.5, negative 0.5 times 400, which is positive 200, times 5, which is 1000, multiplied to this quantity, which is e to the negative 0.5x. And we are dividing that by this quantity here, which is 35 plus 5 times e to the negative 0.5 squared. So this is the derivative of the function which is given here. Example, the incidence of Down syndrome denoted by Y and mother's age X can be modeled using this equation. So this is the relation between the incidence of Down syndrome that can be seen in the newborn when related with the mother's age X is given by this equation. Now what we have to do is we have to find the derivative in first part, and in second part we have to find the derivative at x equal to 30 and x equal to 40. So first let's find the derivative, that is the change in y with respect to x, that is change in mother age, change in the incidence of the Down syndrome with respect to age. When the age increases, whether the Down syndrome that can be seen in the newborn increases or not. We are going to calculate that. So for part A, our function is y equal to, you have a constant in the denominator, you don't have to worry about that. There is the exponential function in the numerator, which is 1.2733 raised to x divided by 1613000. So that is just the constant. So you can keep that in the denominator while finding the derivative. So the derivative will be dy over dx equal to, that constant will remain as it is, 1613000. That will remain as it is. Now this one is the derivative of b to the x. If you remember, the derivative of b to the x is b to the x log b. So in place of b, I have 1.2733. 1.2733 raised to x, so that b to the x, multiplied to natural log of b, that is our base, which is 1.2733. Now, if you want to simplify this, let's see what we get by simplifying this. dy over dx is equal to, so here we have, if we use our calculator to simplify this, we have natural log of 1.2733 divided by this quantity, 1613000. If you simplify this quantity divided by that, natural log of 1.2733 divided by 1613000, what I got here is 1.4979 times 10 to the negative 7, a very small number, and it is multiplied to this quantity here, times 1.2733 raised to x. So that is the derivative in part A. Let's go to part B. So at x equal to 30, okay, if I want to find the derivative at 30, we have to plug in 30 here. So that will be equal to, at 30, dy over dx, the derivative is equal to 1.4979 multiplied to 10 to the negative 7, then multiply to, here we are going to plug in x, so it will be 1.2733, and value of x is 30, raised to 30. So if I simplify this using calculator, it is approximately 2.1057 times 10 to the negative 4, which is like 0.00030 zeros and then 21057. So if you want to rewrite this, 0.000, then 21057. So that is the derivative when x equal to 30. Now we also have to find when x equal to 45. Maybe it will be very small. Let's try it. X equal to 30. This one is pretty small, okay, when x equal to 30. But now we are working at not 30, but 45. X equal to 45, dy over dx will be equal to 1.4979 multiplied to 10 to the negative 7 multiplied to 1.2733 raised to 45 now, because the mother's age is 45 now. And if you simplify this using calculator, the result is approximately 0.0079. So you can see at the age of 30, that was the rate of change. But at the age of 45, the rate of change has increased. Here you have 0.30 and then 21057. At the age of 45, it is 0.20 and then 79. So the incidence of Down syndrome seems to increase with the age.